Today we'll look at one of the exercises from the book Fluid Power Systems. And the exercise that we'll look at today is 16:1, orifice flow 1. So we'll have a look at how we can calculate it and what we can see from this exercise. So let's start, as we want to do with more or less all the exercises, by making a drawing so that we have a feeling of what is it that we are working with. So in the exercise we are given an orifice and we know that the opening area is 10 square millimeters. We are given a discharge coefficient of 0.7. And then we are given the oil density and the pressure difference that we have across our orifice. And I like to write it this way with 10 to the power 5, because then it's clear to me that we have 100 bar as the level. A bit depending on which kind of unit you like to do with, but in the Fluid Power Systems book we use a lot of these, what I call hydraulic units. So when we do this, the first thing we're asked to do is to calculate what is the flow that goes through given these values. And for that we use the orifice equation. And let's put that up. So we have the discharge coefficient, the physical opening area that we have in here, the density of the fluid, and the pressure drop. So if we plug in the numbers, you see that I put in here 10, the area, multiplied with 10 to the power of -6, because then I get it into SI units. So when I'm doing my calculations, I want to do all the calculations in SI units, and then I can always give it back into other units if I like that. And I often like to get that into liters per minute. So we have approximately 63 liters per minute as the flow that goes through the valve or our orifice when we have a pressure drop of 100 bar. So that was the first part of the exercise. In the second part of the exercise we're asked to calculate what is the Reynolds number for the flow going through. And the Reynolds number we can calculate for that using various hydraulic diameters and so on. So if we put up the equation, so what we need is the average flow velocity of the fluid, so the fluid velocity, and then the hydraulic diameter, and finally our kinematic viscosity. So what we can do is, okay, what is the velocity that we want to use? I want to find the Reynolds number just around here going through, and not out here in the full stream. So I like to know what is the Reynolds number in here in the flow that goes through. So therefore I use the flow that we calculate up here, divide that by the area that we have in the opening, multiply that with the hydraulic diameter, so that is the diameter that I have of this orifice hole, and finally the viscosity that we're giving in the exercise. So we can write this up as the flow divided by the area, and then when we want to find the hydraulic diameter we can take the area multiplied by 4 over pi, take the square root of that, and then finally we have the kinematic viscosity that we needed to divide by. Plug in these numbers. We get this number 11,727 as our Reynolds number, and as we know, that is without any units. So what does that tell us? Well, it tells us that we have a highly turbulent flow, which we like to have, because if we go back into the note and look at how did we actually come up with our orifice equation, well, that was built on a turbulent flow assumption. So we assumed that we had a turbulent flow going through our system when we derived the orifice equation. So we really like that we have this high Reynolds number, and we have up here a calculation of the flow that we needed.